Hello everyone, I'm Huang. Today I will be presenting our work towards exploiting CPU elasticity via efficient thread oversubscription. This work comes from the cooperation between Huang University of Science and Technology and the University of Texas at Arlington. At first, let's take a look at what elasticity is and what advantages it can offer for us. Elasticity is an essential feature of cloud computing, which allows users to dynamically add or remove resources in response to workload changes. It helps match system capacity with users' demand and brings many advanced features. For example, high availability and reliability, facilitating growth, automation, and cost effectiveness. Modern cloud providers already support elasticity and implement the on-the-fly resource reconfigurations for existing virtualization techniques, such as virtual machines and containers. Among reconfigurable cloud resources, memory or storage needs to be reclaimed before it can be reallocated to other users, while CPU is mainly an execution worker with a small amount of data storage. It can be quickly provisioned or deprovisioned and only loading or saving little context. It is most suitable for elastic resource management. However, unlocking CPU elasticity is still non-trivial. Traditional applications always match the number of threads to the number of cores at startup and are unable to adjust the number of threads during runtime. Therefore, when the number of cores varies at runtime, applications are hard to adapt to that. For example, when the number of CPUs scales up, the applications will waste the additional CPU resources because of the lack of enough threads. And when the number of CPUs scales down, maintaining more threads than CPUs is believed to incur a large overhead. In our work, we explore thread oversubscription as a general approach to explore CPU elasticity. Users always launch an optimal number of threads for an application, regardless of how many CPUs are available in the cloud. The optimal number of threads is determined offline, as the maximum number of threads an application can use until it stops scaling. Sufficient threads help the application to utilize additional cores when more cores are available. However, when CPUs are in short supply, there are still prohibitive overhead due to excessive context switches, loss of locality, and contentions for short resources. So we studied how different multi-threaded programs perform with or without thread oversubscription. The benchmarks were from PASAC, NPB, and Splash 2, and tested with two settings. First, 8 thread on 8 cores, an exact 1-to-1 thread-to-core mapping. Second, 32 thread on 8 cores, an oversubscription ratio of 4. As shown in the figure, the first and second groups from the left include benchmarks that do not suffer or even benefit from thread oversubscription. In contrast, benchmarks from the third group suffers as much as 25x performance slowdown with oversubscription. The results suggest that thread oversubscription is already a practical approach to explore CPU elasticity for certain applications. However, thread oversubscription is still inefficient for a large number of applications. Then we introduce how oversubscribed threads are scheduled. Linux employs file sharing algorithms to schedule threads on the same core. Each thread is assigned a time slice. The completely fair share scheduler always selects the thread with the smallest virtual runtime as the next running thread. When switching to another thread, context switch occurs to load and safe stress state. Involuntary context switches happen on 2 occasions. For compute-bound workloads, they are switched each time a regular time slice expires. For IO-bound or blocking workloads, context switch occur no more often than the minimal time slice. In Linux, the regular time slice is 3 milliseconds and the minimum time slice is 750 microseconds. Voluntary switching happens when a thread yields CPU or blocks on an event. As oversubscribing threads on a single core cause more context switches, we then study the cost of each context switching. We write a micro benchmark to perform some arbitrary computation or atomic instructions and configure threads to yield CPU to trigger a context switch after they finish the minimal time. Results show that the per context switch cost is relatively stable at 1.5 microseconds on our platform. Since for involuntary switching, each thread is guaranteed a minimal time slice of 750 microseconds. The overall cost is only 0.2%. The direct cost does not increase with the number of threads. For voluntary switching, the frequency of context switching depends on the interval between synchronizations. The frequency of synchronization increases with the number of threads because the work that should be done before each synchronization is less with more threads. Since not all synchronizations lead to context switches, the frequency of context switching is no higher than synchronization frequency. As shown in the figure, most applications perform context switches no more often than every 1000 microseconds, resulting in a CS overhead of 0.15%. The most frequent context switch could occur in facing, which has a synchronization interval of 160 microseconds. Nevertheless, the CS overhead is still less than 1%. Another concern is the effect of context switching on cache performance. We modified our micro benchmark so that each thread travels a subarray between context switches. The indirect cost is calculated by the execution time of 2 threads minus the execution time of 1 thread, then divided by the number of context switches. There are 2 observations. First, for sequential access patterns, the hardware prefetcher is more effective for a single thread as its access pattern is more predictable, and the overhead due to the indirect cost is less than 6%. Second, for random access pattern, thread oversubscription could improve the performance. Realistic workloads are a combination of sequential and random access, and the results suggest that thread oversubscription should benefit caching performance in most cases, with a worst case performance plenty of 6%. To summary, the direct and indirect cost of context switching are negligible or even beneficial. Then we show mechanisms designed for managing threads are inefficient for managing oversubscribed threads. The OS kernel supports fast user space mutex, named the futex, to implement thread sleep and wake up for blocking synchronization. The waiter thread invokes futex wait and starts the sleep process after failing to acquire the lock. It first acquires the lock that protects the futex hash bucket queue. The waiter is then removed from the CPU long queue, in queue on the sleep queue, and its runtime state is changed from runnable to sleep. When the user level lock is released, the lock holder acquires the lock on the hash bucket and moves 1 or more waiters from the sleep queue to a temporary wake-up queue. The lock holder is responsible for waking the waiters 1 at a time, which including selecting a call for this waiter and enqueuing it to the new long queue. The sleep and wake up process can be quite expensive when threads are oversubscribed. The wake up operation first selects the most idle core and inserts the awakening thread to its long queue. This operation requires long queue locking, and the kernel needs to check preemption for the waking thread. When there are many more threads than cores, and a large number of threads are waking, long queue locking and the possible preemption of a recently awakened thread not only cause serialization, but also incurs cascading performance degradation. Moving waiters from the bucket queue to a temporary wake-up queue as additional serialization. Thread sleep and wake up involve frequent state transmissions and leads to fluctuating load. Therefore, Linux performs many unnecessary thread migrations to balance load. Compared with blocking synchronization, busy waiting synchronization provides fast log acquisition at the cost of wasting CPU cycles on spinning. The busy waiting threads repeatedly check to see if a condition is met without relinquishing the processor. When threads are oversubscribed and spinning threads are placed with other threads doing useful work, spinning can burn the CPU time that can be used for useful work. Oversubscription also brings the lock holder preemption problem. The large slowdowns we observe are due to the inefficiencies that arise in the OS kernel when managing a large number of threads on a single core. To enable efficient thread oversubscription, we present two OS mechanisms. The which blocking is a new method for implementing blocking synchronization in the OS kernel. We add a flag thread state to each thread to indicate whether the thread is blocked or not. Threads are not put into real sleep after the thread is enqueued to the bucket queue. We inserts the threads to the end of CPU long queue to keep active. However, blocked threads are skipped during CPU scheduling until thread state is cleared. Since threads are not put into real sleep, when a thread is awakened by full-text wake, its thread state is cleared and it is removed from the full-text hash bucket queue. After thread state turns to 0, a thread resumes normal scheduling and is awakened from virtual blocking. VB brings some benefits. It requires no change to user applications or libraries. The sleep and wake up process is pretty simple. And VB also avoids the influence of frequent blocking on system load and reduces many unnecessary thread migrations. For busy waiting synchronization, we observe some common features among various kinds of busy waiting implementations. A spin loop is a small code segment that is repeated for many times. Especially, spin loops are typically backward conditional branches. Each iteration is quite short, taking only a few circles to execute. And during spinning, branching is predictable with many backward branching. Based on those observations, we present busy waiting detection, a software-based approach for detecting spin loops. BWD seeks to detect futile spinning in an application and deschedule the spinning threads so that CPU circles can be spent on critical threads. BWD implements the last branch records and hardware performance counters, as well as a high-resolution timer to detect spinning. If the readings of last branch record and performance counters indicate spinning, the timer forces the thread of vCPU currently running on the core to be descheduled. These are all experimental settings. Our focus is on evaluating the performance benefits of virtual blocking and busy waiting detection. Performance comparison was made between original Linux with or without thread oversubscription and the optimized system with thread oversubscription. We began with realistic pair benchmarks in containers configured with 2 settings, 8 cores or 8 hyperthreads on 4 cores. Thread oversubscription introduced up to 56.7% performance slowdown under vanilla Linux. The culprits were the loss of CPU utilization and excessive thread migrations across cores. In comparison, we have attained performance close to the baseline without oversubscription, in this case 8 threads on 8 cores. Notably, VB outperformed the baseline in frequency, Ocean, CG, and MG, suggesting that VB could be an effective approach for improving the efficiency of blocking synchronization. Then we dynamically vary the number of available cores and evaluate how oversubscribed threads exploit CPU elasticity. As shown in the figure, EP did not suffer much from oversubscription and benefited greatly from it. Compared to Persian 8 threads, EP with 32 threads can better utilize 32 cores, achieving a 51% performance gain. String cluster and CG always suffered from oversubscription in vanilla Linux. With VB, running 32 threads was never worse than running 8 threads, and always better than with pinning method. Phasing is a bit different. In some cases, it benefited from oversubscription even in vanilla Linux. VB was able to further improve its performance by as much as 34%. While pinning threads to core can hurt performance, as tasks are not evenly distributed among threads. There are 2 fundamental limitations of pinning. First, it is unable to deal with varying CPU count and needs to be repinned threads when CPU count changes. Second, pinning tails of all migrations, even real load imbalance occurs. Compared with conventional parallel programs, cloud workloads usually employ event-based notification mechanisms like ePool. We also implement VB in ePool and test the performance of memcached server. Oversubscription leads to 8x increase in tail latency. In contrast, VB effectively reduced the tail latency by 92% and 60%. We test the BWD with 2 applications with customized busy waiting algorithms. We made 2 observations. First, BWD was able to effectively bring the performance under oversubscription close to that without oversubscription in both container and VM. PRE was not effective for user customized spinning. Second, BWD inflicted some slowdown compared to the baseline, and the slowdown worsened as the oversubscription ratio increased. The overhead is due to 2 reasons. First, BWD cannot identify the raw code and schedule it as quickly as possible. And second, BWD detects spinning at fixed intervals. Nevertheless, BWD is significantly more efficient than the vanilla Linux and contains oversubscription overhead to an acceptable level. So finally, to conclude, we explore thread oversubscription to explore CPU elasticity and identify 2 kernel issues that lead to inefficiencies in managing oversubscribed threads. We present 2 OS mechanisms, including virtual blocking and busy waiting detection to enable efficient thread oversubscription. Our solution achieves an efficiency close to that in undersubscribed scenario while preserving the capability to expand to more CPUs. And our solution is most effective for strong scaling with a fixed problem size. Thanks.